Thank you. Hello, Chicago. So it's a pleasure to be here and to discuss this work with you today. This is joint work with Chris. It's much work in progress, so we'll be very happy to have your feedback on several aspects of on the whole thing and several aspects in particular of the project. It's about emergence of space-time, functional emergence of space-time in quantum gravity. Change the slide. Is it on? I think it's on, yeah.
That is weird.
Can you change the slide?
No? Oh, I can. Try again.
Perfect. Thank you. Sorry. So a project about functional emergence of space-time in quantum gravity. Since there are many research programs in quantum gravity that suggest that space and time, or in some sense, may not be part of the ontology of these theories. There are two main sets of conceptual issues related to this fact that space and time, in some sense, disappear in these approaches to quantum gravity. The first one is about a threat of incoherence, of empirical incoherence, and the second set of issues is about how to characterize a physical ontology as described by these physical theories without space and time. Physical ontology without space and time somehow. These are the two sets of conceptual worries that one might have in this context. Here in this talk, I'll mainly discuss the first set, and at the end of the talk, I'll mention a few things about how to characterize physical ontology without space and time. A few ideas how to do that. Again, doesn't work. So maybe you can just change. Thank you. Now, about the threat of empirical incoherence. In philosophy of physics literature, this idea of empirical incoherence comes actually from the debate about the ontology of quantum mechanics. And I'll mention the analogy with this debate on the ontology of quantum mechanics several times and see what it brings to the debate here in quantum gravity. The idea in the non-relativistic quantum mechanical case is that there are conceptions, realist conceptions, about the ontology of quantum mechanics, where you take the central theoretical entity, which is a so-called wave function or quantum states, and this wave function is, the details are not so important. The important fact is that if you have a realist commitment with respect to the central theoretical entity of quantum mechanics, then this entity is not defined over usual four-dimensional space-time or three-dimensional space. It's an entity, it's a kind of field defined over an abstract space, a huge dimensional space. And the question then is, or a possible word that has been raised in this context is that if you are realistic with respect to this entity in quantum mechanics, then you have a problem to account for empirical evidence. Hence some kind of worry that the evidence that might justify you believing in quantum mechanics in the first place, you're not able to account for them. And here it's a bit similar. Here are three claims. The first one is that the first intuition is that empirical evidence somehow for physical theory always amounts or involves somehow a physical object having a certain position at a certain time, position in space, like a pointer, for instance, pointing to a definite number, spin up or spin 1/2, for instance, as a result of an experiment, for instance. It seems that all kinds of experiments that we can make then at some point involve an object, a physical object having a certain position in free space. And this is precisely the intuition behind John Bell's quest or need for local, what he called local variables in the ontology of quantum mechanics. Variables is a word for what there is in the world according to your theory, in a realist perspective, of course. And local means that what there is somehow has to be in terms of things located in free space, associated with a bounded space-time, finite space-time region. Otherwise, you can't account for empirical evidence in the first place. This was targeted against wave function realism, the disposition that I've just described before. And then it seems as a consequence that if you accept this is kind of intuition, direct intuition, as Bell did, then it seems that as a consequence, empirical evidence involves the fundamental existence of space and time. Hence, therefore, any kind of theory denying the fundamental existence of space and time undermines the possibility of its own empirical justification. This is the kind of argument. And there's a similar argument in non-relativistic quantum mechanics. And the word here is that you have exactly the same kind of problem, or even worse, in the case of these quantum gravity approaches, which seem to deny the fundamental existence of space and time. And for instance, this of course comes in different ways, depending on the approaches you're looking at in quantum gravity. And this has been discussed, for instance, by Nick and Chris in this paper. Perfect. Now, just from a physics point of view, this is old news in the sense that every time you develop a new physical theory, then you have as a constraint that you have to recover old physics, old empirically successful physics. So this is just the usual methodology in developing a new in physical theorizing. And here, of course, you have this in the case of quantum gravity, and the constraint is just you have to recover the special or general relativistic smooth space-time description of the world. So from the physics point of view, the story is clear. And it's mainly technical issues involving approximation, limiting procedures. So there is a lot of technical tools, and the story is not clear, and people do not exactly know how it goes. But this is the technical side of the problem. Now, from a more conceptual point of view, the question is whether this is sufficient to meet the challenge of empirical incoherence. Because in the case, again, take the analogy with the case of non-relativistic quantum mechanics and this position believing in the existence of the wave function, this field in this abstract space, as the reference to your theory, what exists in the world according to quantum mechanics, then of course, people who take this conception, wave function realism, have a story to tell about recovering empirical evidence, of course. And I'll discuss that a little bit. But in this context, people have questioned whether, or raised worries, whether having just a mathematical derivation, a way to explain how you recover the old formalism, in a kind of mathematical way, even if it's well defined, whether that's sufficient to really account for your experimental evidence. And this worry has been raised in the case of non-relativistic quantum mechanics by Tim Modlin, for instance, and other people arguing against this position called wave function realism, against viewing the ontology of quantum mechanics as being constituted by this field in this abstract space. So he would say, for instance, that a pure mathematical derivation, a mathematical account of the old physics is not enough. You have to have somehow a physically salient derivation. It has to be physically meaningful. It's not enough to just give a mathematical derivation of the old theory. That's a bit the worry there. Of course, in non-relativistic quantum mechanics, the idea is that if you have only this field in this abstract space, you're not going to be able to recover, in a strong sense, three objects in free space. What seems that we see around us and what we have in the labs. You might have a mathematical way to try to account, and that's what people have done in the case of wave functionalism. but it's, according to people like Tim Morgan, it's not going to be enough because these mathematical relations are not going to be physically salient. That's a bit the worry. About the second set of issues, there are two aspects to it. The first one is first of all, how to characterize the fact that we have several things, because we don't want to speak about just a kind of gunk at this fundamental level. We'll see in the theories we're going to discuss in this talk. We still want to keep this notion of having several things, but the issue here is how to characterize this plurality in non-spatial temporal terms. Another aspect is the worry that we end up with a kind of ontology which is no different from an ontology of abstract mathematical entities. And the worry is then how to characterize this ontology, the physical ontology described by these theories, when the entity described are not spatio-temporal in some genuine sense. And of course, as you all know, there are two standard criteria for things being concrete as opposed to abstract. The first one relies on space-time, and it says that concrete physical entities are in space-time, whereas abstract mathematical ones are not. But of course, here we cannot use directly this criterion because we are dealing with the space-time itself, or possible case where space-time itself is not there, is not fundamental in some genuine sense. The second criterion relies on causation, and it says that concrete physical entities are causal in some sense, whereas of course mathematical abstract ones are not. But this, of course, in this case, in this context, it requires some kind of notion of causation without space and time, non-spatial-temporal notion of causation. This is, of course, non-trivial. Standard notion of causation, standard account of causation, already had a hard time in physics, in standard physics, and here we would need a non-spatial temporal notion of causation in this context. But we'll see that at least in the context of one specific approach to quantum gravity, maybe that's what is going on. But we'll see. The idea now, roughly, is that these two standard criteria suggest a kind of mixed strategy and trying to combine these two standard criteria. And the strategy is the following, is to focus on the space-time or space-time-like functions or roles in some broad sense, more functional than causal sense, that the entity is described by the quantum gravity theories may instantiate at the fundamental level in some circumstance, like in low energy limit, for instance. So the idea is to try to focus on the roles of the functions they can play in certain contexts, and to see whether that would be enough to meet the challenge of empirical incoherence. That's the idea. And of course, the idea is also to see to what extent we can use the tools which are out there about functionalism in different areas of philosophy of science, and to see to what extent we can use these tools here in this context. And we'll see, I'll discuss this a little bit. That's exactly one of the strategies which has been implemented in the case of wave function realism, in the case of the ontology of non-relativistic quantum mechanics. And the idea is here to what extent we can extend this here in this case, and to investigate what extent it might be helpful. Just very quickly about functionalism. I'm sure you know a lot about this in philosophy of science. It's of course a family, a variety of different linguistic and metaphysical conceptions. The generic idea is that the relevant predicates or properties are understood in terms of their causal role they play in the context where they're defined. This is the idea, for instance, think about philosophy of mind. And the aim is to provide a kind of understanding of the links between qualitatively different levels. For instance, think about the mental level and the physical level in the philosophy of mind, and functionalism in philosophy of mind. And here the analogy would be that here we are trying to understand the link between two different, qualitatively possibly different levels, the quantum gravity level and the smooth relativistic space-time level of general relativity. That's the idea. So there is some kind of analogy here. we are not the first to think that functionalism can be useful in philosophical physics. Recently, several people have been using kind of functioning strategies in philosophical physics. For instance, David Wallace from Oxford. His functionalist emergence of rules, patterns, structures in the context of the emergence interpretation of quantum mechanics. Leonard Knox, Spacetime functionalism in the case of classical spacetime theories, and David Albert's causal functionalism within this position of just this conception I've just mentioned, wave function realism. So he typically has had the idea of trying to use a kind of functionalism at the level of this wave function realism in order to recover the three-dimensional world we have, things located in three-dimensional world. That was and here's a quote from David Albert in the context of his functionalism, his use of functionalism. This is very standard. The thing to keep in mind is that it is to be a table or chair or building or person is at the end of the day to occupy a certain location in the causal map of the world. This is standard from the functionalist point of view. The thing, and then this is specific to his approach to wave function realism and to the case of quantum mechanics. The thing to keep in mind is that the prediction of geometrical occurrences, so three objects located in free space, Bell's local variables, for instance, is at the end of the day a matter of dynamics. So we'll see that's a disanalogy with the case of quantum gravity because the issue of dynamics is going to be more complicated in the case of quantum gravity. But in the case of wave function realism, he would say that the dynamics of the wave function in this abstract space, which could, the way the wave function behaves, which could account for the occurrences of three objects in free space, local variables, the thing we see around us. That's the idea. Now, our idea is to extend this to the case of space-time in quantum gravity, and the strategy is that trying to understand relevant space-time features, for instance, the features that we need for accounting in order to account for empirical evidence in terms of their functional role, and of course it need not be causal in kind of more general sense. And the intuition is, and the good thing somehow would be that space-time would not be fully recovered or need not be fully recovered to merge, for instance, in some strong ontological sense, because this was the worry, of course. You all may know that the notion of strong ontological emergence is non-trivial. And here, and we'll see that's one of the objections to the whole project is that seems to be very hard to come with the idea that you can have space-time things or things with spatio-temporal features emerging from something without any kind of spatio-temporal features in the first place. This seems to be very, 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 very difficult. Think of an example in philosophy would be Leibniz, for instance, starting from things out of space, non-spatio-temporal, and how you really recover in a realist fashion, of course, not with some kind of idealism, physical space and time. But here, if this works, if this makes sense, then we wouldn't need that. But of course, the question now is how that works and so on. That how does it work in concrete cases? And of course, we don't have a full, complete theory of quantum gravity, so we have to look at the best candidates, so to speak. And here, two candidates we are looking at are loop quantum gravity and causal set theory. I won't go into too much mathematical or physical details. I just want to focus on the aspects related to the use of functionalism with respect to the emergence of space-time in these two cases. That's what we're going to discuss now. So, loop quantum gravity, a few key points. It's the very, very briefly, without the details, we don't need too many details here, which just applying the same old quantization recipe to general relativity. And of course, there's something new, and this use of these new variables, so-called artificial variables. And what is important is that what we get if we do that to general relativity are these spin network state, or which form a basis for the state space of the quantum theory corresponding to the quantization of GR. And so-called Hilbert space, but that's not so important here. The idea is that the states we arrive at, which are going to be the states of your quantum gravitational field, if you want, are going to be described in this approach by these spin network states, and they can be associated in some nice natural way to graphs, to a graphical graph representation, not embedded in space-time, as we will see. And the key result in the last maybe 20 years, or since the start of the whole approach, loop quantum gravity approach, is that these spin network states are eigenstates of the corresponding area and volume operator. And these operators have discrete spectra, and this is the basis, the basis for all the claims you can hear within loop quantum gravity community that space and time are discrete to some extent, and then we will see disappear in this approach. We'll discuss that. But of course, first issue. And here, it strongly depends on your interpretation of the first place of these operators that we can construct by analogy to the classical case as genuine volume and area operators in this case. And this is highly non-trivial, as we will see. It requires already having a certain way of looking at the interpretation of the quantum aspect of the theory. And this is non-trivial. There is also, I'll mention this a little bit, but not too much in it. There is a covariance approach or spin form approach to the theory, where then the dynamics, because here it's only at the kinematical level, and then the question is, of course, how the dynamics unfold, and this is highly problematic for different reasons. One of them is, of course, that we are quantizing space-time itself here, so it's difficult to have an easy, accessible notion of dynamics. And there is a covariant approach to the theory where dynamics is understood in some kind of perturbative way as transition amplitudes between spin networks. So spin networks would be states, if you want, of the gravitational field, or space, if you want, quantum state of space. And then the question is how it evolved. And this would be described by the spin forms. But we will see that the analogy with space and time is a bit more complicated. Here is a standard picture that you can find in many papers on loop quantum gravity, for instance by Carlo Rovelli. Here, this will be a graph associated with a spin network state, nodes and links, and you can define them in a kind of combinatorial way without embedding them in a space or in a manifold. And here, the corresponding image of your granular space-time, if you want, the chunks of volume or atoms of volume would be associated with nodes, and atoms of surface would be associated with the links. And then, of course, through the spectral analysis of the operators of volume and area, you can associate in a well-defined way the atoms of volume to nodes and surface to links. And the quantum numbers associated to the nodes and links would define the corresponding volumes. That's a bit the very roughly the idea. And of course here you can see the graph is a kind of dual, if you want. It seems that you still have some kind of spatial-temporal thing here, especially in this kind of graphical representation. But there's limits to this understanding in spatial-temporal terms for several reasons. The first one, as I said before, these graphs, these spin networks, are not embedded in space and time. The links here should be understood in a metrical way that do not give you a distance between the nodes. And moreover, the important point is that two nodes here connected by a link, connected by a link, need not be correspond. If you take the corresponding emergence spacetime, for instance, they need not to correspond to adjacent in a metrical way spacetime events. So two nearby, in some non-metrical sense, nodes of the spin network need not correspond to two nearby general relativistic events. Some kind of new non-locality, if you want, here might emerge at the fundamental level. And an additional problem for the spacetime understanding of these entities is that the generic quantum states are going to be superposition. So, as always in quantum mechanics, strictly speaking, this is you have superpositions of spin network states. A generic state of the quantum gravitational field is going to be a superposition of whatever that means of these spin network states. So you see that putting all this together, it seems fair to say that standard space-time was, in this case, localization is not available at this, or straightforwardly available at this level for these reasons. Now I'm going to focus now on this notion of localization. Local variables, remember John Bell's notion. What exists has to be local. It has to be associated with the bounded finite region of space-time. And so the notion of empirical incoherence relies really crucially on the fact that empirical evidence, empirical data involves spatial temporal localization. The point has to be somewhere, pointing somewhere. But the local quantum gravity program is based mainly on GR, and one of the important consequences of GR is that there is no external fixed space-time background with respect to which you can localize your pointer for physical systems. And in this general relativistic context, already at the classical level, it seems that localization is not inherently spatial temporal. So in the sense with respect to a background space-time in particular. But firstly, fundamentally dynamical, so with respect to dynamical systems. You can choose, in the classical case, you can always choose the local gravitational field, of course, the metric field, and localize things with respect to this metric field. And in special cases, for instance, like in this room, it's going to be a flat metric and so on, so everything looks like we can localize things with background space, for instance. But in the general case, and for the metric gravitational field itself, you cannot of course do that. Localize for instance, the gravitational field with respect to space-time, for instance, because the gravitational field is itself encodes itself space-time features. That's the idea. So it seems that from this dynamical point of view, the heart of GR, for instance, the notion of localization at the basis of empirical evidence is really dynamical rather than spatial temporal, explicitly spatial temporal. And now we can have a functional perspective on this notion of dynamical localization. The physical localization, physical sense of gauge invariant in the GR sense localization is instantiated in GR first through functional relations among dynamical entities. That's the idea. In the case of classical GR, I'll give you an example. Localization is a non-trivial task, but we can have a genuine notion of localization, for instance, here of the electromagnetic field, with respect to, I give the example here of the Bergman-Komar procedure, with respect to 4 independent scalar fields. So you can localize, if you want, the Maxwell field with respect to other scalar fields. And this is a genuine, the scalar fields here, in the Bergman-Komar case, they are going to be constructed out of they're going to be functional of the metric field, but they are going to play the function of physical space-time points, physical in the sense of gauge invariant. It's not about a system of coordinates that then you can change and then you change your description. Here it's everything at the level of the manifold, if you want. And so what the procedure does here is if you take these scalar fields as physical systems, you're localizing a physical system, namely the Maxwell field, the electromagnetic field here, with respect to other dynamical fields. That's the idea here. And this is in a gauge-invariant way. And the analogy here in the loop quantum gravity case would be that the node and links of spin networks in certain specific cases are expected to play similar localizing function in the classical limit, for instance. But of course, not always, because the links, the adjacency relation, as defined by the links again, they may play the function of spatial relations, so that the node would play the role of, or these links would help you to localize things, but not always. Of course, as I said before, sometimes two nodes related by adjacent at the loop quantum gravity level could be mapped into two far apart in a metrical way in the stellar classical spacetime. But still, these nodes and links could play some kind of localizing function in certain cases. I'm going to just give you an example of the semi-classical limit in loop quantum gravity. It's just a few cautionary remarks, because it's ill understood yet, and there are many technical issues that need to be solved. And from a conceptual point of view, it seems almost hopeless to try to understand the classical limit of a quantum theory without addressing the measurement problem in the first place. But anyway, I'll try to say something here without addressing the measurement problem. But keep in mind that at the end of the day here, in the case of any quantum theory, you have to say something about that. It's linked to what I said before about the interpretation of the operator in terms of volume and area operators. But here, the aim would be, the minimal aim would be trying to see whether a functionist perspective on the specific issues related to the absence of space and time can help. But keeping in mind that if you want to have a full description of your ontology according to a quantum theory, then you have to address the measurement, say something about the measurement problem. Okay, just an example how it works in loop quantum gravity. There are these so-called wave states, which are specific special spin network states with specific large-scale behavior, that they behave at large scale in a spatial temporal way, so to speak. And how? It's just that there are going to be, as I said before, spin networks are eigenstates of the area and volume operators. And the idea is just to say that there are specific spin network states with the classical eigenvalues for area and volumes. So the eigenvalues are going to be just the classical values as defined by a classical metric. And so the idea here is to say the detail, of course there are two corrections, but the details are not so important. The idea is here at large scale, so in the appropriate limits or circumstances, then these, whatever is described by these spin network states is going to play the metrical function of classical volume and area. That's a bit the idea, through these relations here. These spin networks are then called wave states. And worry that has been raised is that the relationship is many to one, so different spin network states can play the same, can correspond to the same volume and areas. But of course, as you all know, from a functionalist perspective, if you take this from a functionalist perspective, this is no worries. It's just what is called in different domains of philosophy of science, multiple realizability, for instance, that you have different spin network states playing the same functional space-time-like role, if you want. So that can be a nice kind of nice feature of this functional approach here. And of course, you can apply, or the idea would be then to apply this kind of functionalist understanding to the other approaches of the semi-classical limit, so-called coherent states, or in the covariant approach, where spin forms in certain cases are expected to mimic somehow a kind of classical specialization of classical spacetime, and then through this classical specialization, the idea would be that the spin forms, or what is described as the spin form, would play the function of a discrete spacetime. And then in the classical limit, you recover smooth spacetime, in the continuum limit. But that's, I think here is the main idea of trying to apply the functioning strategy to this semi-classical limit here in the loop quantum gravity case. The second study case is a causal set theory. It's very intuitive. Here, the idea is that the fundamental structure is discrete, and so you have a set of events, if you want, and they are partially ordered. You have a partial order on this set. And the idea, of course, is that this ordering is somehow causal. And the motivation behind that is are several results in classical GR, without the details again, but by the way, these results are extremely nice from a math point of view. It's that if you have the causal structure in some sense, then you can recover the rest, or the rest is determined to some extent up to size to control more factors. So geometry and so on. So that's then the idea is that if you have the causal structure in a GR sense, then you have the rest up to control more factor up to size. And then the idea is to pick the physically the subset of the physical causal sets at the fundamental level. Here is a graphical representation of so-called Haas diagram of the causal set. You have the nodes between the causal set events, and the links are the relation not implied by reflexivity and transitivity. Remember, it's a partial order, so it gives you a bit an idea of what it looks like. Again, we could think of, similar to the case of the spin network, a graphical representation of the spin network, we could think as this kind of entity as being spatio-temporal in some sense, but there are several ways in which it departs from classical space-time. Of course, the causal order somehow mimics some kind of temporal order, but it's different. First of all, it's discrete, and you don't really have a now or a flow of time, so it's going to be kind of discrete B-theoretic version of relativistic time. And of course, these relations are not metric. You don't have a metric at this level, so you have no duration. The case of space is even worse, because if you try to define space as, for instance, the set here of, without the details, of unrelated events, so-called anti-chains, then you see that these maximal sets are going to be unstructured in a very strong way. No dimensionality, no metric structure on these sets. So trying to define a now, for instance, or space is going to be very challenging. And for these different reasons, it seems that we've lost genuine space-time features at this level, and that the relations described here are causal rather than spatio-temporal. And of course, the challenge then is trying to recover the smooth space-time of GR, of general relativity, from this discrete description. And there are several ways to do that. One intuitive way is trying to find what is called a faithful embedding, that is a map from the causal set to relativistic spacetime such that it looks like a manifold, and it of course preserves the metrical structure. For instance, here, if x is related to y, then x should be mapped in the causal path of the image of y through this embedding. That's a bit the idea and the challenge. Now, without, again, there are many details to be discussed and interesting details. That's not the aim here in this talk. But assuming that we can do that, just a huge challenge already, and it's not trivial. That's unique. It's a famous so-called Haupt for Mutung and so on. Then the question, remember, Maudlin's challenge. The question is it sufficient to establish the emergence of space-time in a genuine way, or is it just a necessary condition but not sufficient? And here the functionalist approach would say, now this is, if you have all that, of course it's not clear that we have, but this would be sufficient. And the emergent structure through this function, for instance, would gain physical salience by virtue of the space-time-like function it plays in the appropriate limits, where these embedding play its role. And he would be somehow have a case of empirical evidence in terms of space-time-like localization, but at the fundamental level would be a kind of causal localization at the level of the causal set. And this seems to echo somehow Albert's strategy that remembered, for instance, when he said in the previous quotes that the table is to be a table is to occupy a certain location in the causal map of the world. That's the usual story. That would be something analogous here. I'll finish with just a few comments about the second set of issues about the characterization of physical ontology without space and time. Remember the word that what makes such an ontology as described by causal sets, by spin networks and so on, without space and time physical, in contrast to an ontology of abstract mathematical entities. So spin network states what makes them physical rather than just mathematical entities. And it's interesting because exactly the same can be applied to, again, the wave function. There are people, like in the tradition of John Bell, again, saying that the wave function is the wrong way, the wrong understanding of the wave function as to try to reify the wave function. This is just a mathematical device, like the Hamiltonian and so. What is there, what is physical, are always local variables, giving you an account of measuring apparatus, pointers, things around you, and so on. And then in the mathematical apparatus of your physical theory, you might have wave functions, Hamiltonians, whatever. But that's mathematical entities, not physical ones. And the question, and of course, mathematical entities can be defined over abstract space. That's fine. And the question here, to what extent do we have the same problem here? But the idea of the functionalist approach here would say, kind of deflationary attitude would say, well, the structures described by the quantum gravity level, spin networks, spin foam causal sets and all, would be concrete or physical as opposed to abstract mathematical in virtue of the space-time-like roles they would play in certain circumstances. That would be the idea. And an abstract entity would never play such kind of role, whereas these entities described by these theories, in certain cases, they play these functional roles, these space-time-like roles, such that we have functional 3 objects in 3 space around us and so on. That would be a little bit the idea. And it's in virtue of that they are concrete. There is an objection recently by Alison Hay in a recent paper. Again, this is in the context of non-relativistic quantum mechanics. Again, she's arguing, it's a bit perverse here because she's arguing in favor of wave function realism, but she's considering first different objections against wave function realism. And I think she has an interesting point here. She is referring now to the proposal trying to make sense of local variables starting from this abstract field or wave function over an abstract space, like Albert's functionalism. And she says, but this proposal are not entirely convincing, although they make some headways in indicating how the wave function, so this abstract field over the abstract space, may possess some of the features of 3 objects. This is not adequate to demonstrate how the wave function may actually constitute this type of things. So it maybe gives you an idea how it works, but never will the local variables, the things around us, be constituted by the wave function. So that's dead end. And she continues to see this. It may help to consider, this is very familiar to people working in philosophy of mind, for instance. Standard argument. It may help to consider that with holograms. A hologram of, say, a person may possess many features to let it present the appearance of a person rather than something else, a chair. But it produces such appearances that it has the relevant features, doesn't thereby entail that it actually constitutes a person. What we need is accompanying account, not of how a particular evolving wave function may have features in common with three objects, or features that correspond to features of three objects, but a accompanying story as to how a wave function is capable of actually constituting such objects. So she's looking for a way or an account of how, beyond this kind of functioning story that we can have, how really three things in three space can be constituted by this kind of abstract entity. And it seems that we might have the same problem here in the quantum gravity case, of course, and even worse. So there are two related aspects, and I'll finish with that. Again, in the quantum gravity case, the objection would be how something non-spatial temporal can constitute things with space-time features. For instance, localized in space and time. This is the usual objection. And the second aspect of Alice Anne's objection is that it seems that, again, this is well known to people working in philosophy of mind, functional rules do not expose the nature of things. So even if it has derived functional rules in certain cases, it won't tell you what the thing is, or it's not enough. But here, a possible answer from the kind of functionalist strategy here in this space-time case is that constitution, in the sense she's looking for, so like a Lego building blocks of the pointer through the wave function or through non-space-time spin networks or whatever, is not what we need here, I think, or is not what is really needed to account for the appearances. And the application here of the functionalist tools is with respect to space-time features, but the quantum gravity things described by the quantum gravity theories may have other features, of course. And here the game is only to apply this functionalist kind of functional analysis in order to recover the three features, three-dimensional features of things around us and empirical data. That's the big kind of strategy that we can apply here. But again, that's very, very rough and preliminary. And of course, I'm waiting for your ideas on that. Just a summary, and then I'm done. The idea here in this talk was to apply a standard functional strategy to avoid the threat of empirical evidence in the quantum gravity case. I've discussed the analogies and disanalogies with the case of quantum mechanics. And the idea, again, is that the fundamental quantum gravity entities can play the relevant space-time roles, in particular those in line empirical evidence. And I've discussed in the case of localization in quantum gravity and in causal set theory. And the question of physical salience, I think, is not something a priori, but theory dependent. Modern's idea seems to be that that something is physically salient if you have your ontology defined in terms of local levels, so things in free space evolving in time. Otherwise, it's not going to be physically salient. This seems to be highly a priori, and I don't see why we should apply this kind of methodology here, especially if we are dealing with the nature of space-time itself. And the idea is to investigate to what extent function can provide interesting tools. And of course, beyond localization, one important part of the project here is trying to identify what we need to recover, what kind of space-time features we need to recover in a clear way, an explicit way, in order to account for empirical evidence. And finally, these quantum gravity entities are physical in the sense through the space-time functions they play. And maybe the kind of constitutional argument objection to this kind of approach might not be relevant here, since we don't really need to have constitution of space-time things out of space-time, out of non-space-time entities. This is not what we are looking for. Thank you very much for your attention.
Okay, so do you want to field your own questions? Would that be possible? So you lead the discussion.
Yeah, sure. And we will forward the hard questions to you.
Vincent see us, so if we raise our hands, he can.
Yeah, I can see you.
You should be able to do that. Yes.
Okay. Cool.
What is where we should go for the question Q&A?
Chicago people, you have questions?
Yeah. Should we go first?
Yes.
No problem.
So this was. Can you hear me okay?
Yes.
Very good. So let's see. So this was right. So towards the end, you wanted to say that. I think there was a slide that said. Let's see. Sorry. You were talking. You said. I guess you were equating. Sorry, the sort of functionalist solution with physical salience.
Yeah.
So I guess that's not. I mean, this is. I don't want to sort of launch on kind of my agenda, but you were talking about some of my work. Maybe it's a bit fairer. So I mean, I think when Alyssa, when Nay is talking about constitution, that's what I would talk about. Whether there was physical salience. Okay, so let me put the question this way. Okay, sorry, you put me a little off guard. So think about the case, the sort of Albert and Maudlin debate about wave function realism. You've got sort of the phenomena, the 3D phenomena. Part of the deal is there seem to be two kind of theories, two ways of thinking about what's going on there. One is, well, there really is just sort of wave functions there really is just three-dimensional space, the kind of Maudlin approach. And then there is sort of configuration space, that's what's real. Both of those approaches are functionally adequate, right?
Yeah.
So are they both physically salient? I mean, that just seems wrong. I mean, one of them should be the right, one of them is physically salient because it's the right way. So if you just limit if you just sort of equate the physical salience with sort of functional adequacy, that seems like it's not, I don't know, that doesn't seem like enough.
Yeah, I agree, but maybe that's precisely this analogy between the standard quantum mechanical case and the case of quantum gravity, where we are dealing with space-time itself. In the case of the ontology of quantum mechanics, if you have, and I think that's more or less Maudlin's approach, if you have an ontology in terms of local variables, then of course, with the same functional adequacy, then of course you should choose the ontology of local variables. The issue is that it doesn't seem trivial to find an ontology of local variables in the case of quantum gravity.
Okay.
Therefore, the only guide, I would say, would be in the quantum gravity case would be then what remains is only the functional adequacy as I define it. You don't have the local variable stuff anymore in the quantum gravity case.
Okay, good. I mean, I think I totally agree with that then. So you really do want to prize apart the sort of functional adequacy from the physical salience. They're not the same thing. I mean, one is evidence for the other, say, something like that. I mean, that's the relationship.
No, correct. I agree. Yes, correct. And maybe what I said wasn't clear, but I think I agree. Yes.
But then that seems like the answer. I mean, maybe that was that just seems like the answer to Nay then is, well, look, in this case, we have to figure out what's physically salient, but, as you say, in the wave function case, well, we seem to be in 3D space. That seems like a pretty good reason to think that's physically salient.
Yes.
But we don't have that, so all we can really go with is the one functional story we have.
Yes. Yeah. I agree.
Okay. Well, then we agree. That's correct. Okay, so do you have
No, I don't think I have any second questions and thoughts. I think it's a little bit beside the point, though. Because I was just thinking about, because I'm thinking more about how emergence of space-time would appear in the string theory context. So I was kind of looking for similarities. And I also think that this functionalist view on what plays a space-time role is important in that context as well. And then I also have kind of a comment that maybe should, I mean, if it's pretty obvious though, but if space and time is not in the fundamental ontology, we don't have to require that it appears in all solutions, that there is something playing the space-time role. It just has to occur that there are such solutions playing that can describe our world or something like that. We can also have a lot of non-spatial temporal solutions in that underlying fundamental theory, whatever that is.
Yes.
But that's kind of more common.
Yes. But the thing is, remember, the aim of the game here was to try to reply to the kind of empirical incoherence objection, which is basically the idea that without space and time in some strong sense, then you cannot even account for the empirical data justifying your building.
What I said wasn't criticism. That was
yeah. But of course, then you want to go beyond that, and of course, your quantum gravity theory, string theory, whatever, is going to describe non-spatial temporal features or non-spatial temporal entities, and that's precisely what's going to be new, I think, with respect to other areas of physics.
We never introduced ourselves to the audience then. I just wanted to say hi, I'm Nick Huggett. So.
Hi.
Hello everybody. I think
Yeah,
was that on your side as well?
Can you hear us?
Yeah.
Okay, good. So thanks for the talk. I'm just to introduce myself. Just like you purely metaphysician, so that would be really dirty metaphysics. My question. I'm sorry for that. So one thing that puzzled me with the talk is your attempt to give a definition of what is concrete in terms of your functional model. So you gave, I don't remember the slide exactly. You explained, supposed to be explained that the fundamental structure of the nodes are concrete in virtue of the space-time role, basically the functional role they play.
Because the idea is that you cannot apply the standard criteria, and being in space-time or being causal in some sense.
I got that. So frankly, given your functionalist model, I would have expected you rather to not trying even to analyze concreteness and take the basic fundamental things as just being concrete.
Yeah.
Briefly, explaining why I think it's a better move actually. Because I suppose we have, I think, strong beliefs according to which concreteness or not is an intrinsic feature of things, and it's also a necessary feature of things. It seems very strange that whether something is concrete or abstract can vary. And here, maybe you have, maybe your nodes and the basic structure, they play this role at the type level, but not necessarily at the token level. So maybe that some tokens at the basis, they don't play the role for the space-time because it seems that your realization is that it's in type time. Right. So it might actually be the case that even at type the role can change. I don't know what's your view about causal laws of nature guys, what the model feature of laws of nature, but some people who maintain qualitism think that that actually the rules of entities can change, and obviously if you have qualitism, then it's completely extrinsic and contingent whether the basics should play this role or not. So that's why it seems to me you will have whole sorts of problems if you try to define completeness like that. Debates you don't want to enter in. Or if you just posit that it's complete, it would be better.
May I say something?
Yeah, sure.
So, thank you very much. So, what about the following sort of amendment to what was perhaps written verbatim on the slide? So what was on the slide is not meant as a definition of what it is to be concrete, but as a definition, I think we should be happy to accept something along the lines you suggest. But what was on the slide would then do the sort of the additional work of showing that this definition of what it is to be concrete latches up or connects in the appropriate sort of way with concreteness as it's traditionally understood in sort of more spatio-temporal, the usual kind of terms. Because, you know, I can define concreteness as however I please in my theory. I say, okay, this is concrete, but then, you know, there still seems to be the question, well, you know, why concrete? Why do you choose that word? In what sense does it, what's the relationship of your concreteness to the more standard versions of concreteness? And it's important, of course, of that project to show that no, it connects up. That is very much the central claim.
Can I follow up on that? So that's really wide metaphysics, but suppose, I mean, we can understand the mathematical object, in particular, singleton sets, as well emerging from concrete object, but they're abstract. So suppose some guy comes with and reverse the order of explanation, the way you want to do, but they do it for the order between singleton and the member. They say, well, actually, what's fundamental is the singleton and the particular object that emerge or from the singleton like that. And then the guy can say, well, actually, my singletons are concrete because they play this functional role, which is to make for concrete thing that emerge from them. That would seem to be silly, no?
Yes.
Okay. So it seems that it's not explaining the thing at all. It seems to me. But anyway.
Not sure. I'm not sure. So your proposal would be not to enter into the debate in the first place.
That would be my view.
Okay. And again, to be sure I understood the possible worry is that if we understand concreteness in terms of possible function or roles that certain things can play, then the worry is that it's not exhaustive, or
the worry is that it's too extrinsic.
it's too extrinsic.
No. You want the concreteness to be really into the things you call concrete in a way, not to come from the rules they play.
It's interesting because it connects in general to the usual objections against functionalism in general. Think about the case in Geometrical mind.
Maybe I don't know this debate.
I mean, the usual worry is that, okay, you guys are doing quantum gravity. You have a theory of quantum gravity. You can write it down. What you write down is a bunch of symbols, Greek letters, in combination with you know, sort of squiggles that you don't find on your keyboard, and then you're asking, okay, by virtue of what does this give me something that's space-time-like, or does give it, you know, give me the sort of features that we would expect from a physical theory. A priori, this is just these are just, elements in a high-dimensional Hilbert space and things like that. Now, of course, you want to say, no, you're missing, you're making the basic mistake of mistaking the representation for the represented. There is something that is represented by that mathematics. But then, the question is, okay, what is that? What is that thing that's represented? Why should we think that this is a physical thing? And why should we think that it is the physical thing that gives rise in the appropriate sort of way by, combining its sort of micro parts in the appropriate way to give rise to the world as we know it in the large scales? And in a sense, this is addressing this question. That's the idea anyway.
Because if you think then, because your objection, the worry is very general in the sense that it would be against, it would also concern the two standard criteria I mentioned. Space-time and being spatial or causal are also extrinsic in your sense.
Well,
would that be correct? Or?
Well, no, I mean, what do you think? Yeah, I mean, I suppose there are general problems about definitions of concrete. The question is whether you really need to do that. Whether you really need to define concreteness to come for the.
I mean, very concretely speaking, the reason why we put that in there is because we've gone to conferences presenting parts of this material, and people like Michael Esfeld will check and say, "Whoa, but if you tell me this is a physical body in space that moves according to the following dynamical law, like write down Newton's law of motion and stipulate extended bodies in space and time that bounce off one another and things like that, then this is obvious, this is physical stuff, and that the laws are somehow capturing what the dynamics that's governing these physical bodies, and I have no problem understanding what's going on and understanding what this is a theory about. The ontology is very clear and straightforward. When I look at your things like these theories of quantum gravity, I don't have not only do I not have rigid bodies and billiard balls moving around, I don't even have space and time now. I really don't know what I'm talking about. In what sense is this a sort of a physical ontology? That's the question, as opposed to, for instance, just a bunch of mathematical objects or who knows what, something else altogether.
So the question is more whether it's kind of natural entity, a kind of physical entity, than whether it's concrete, which I think is more tricky to define. So.
Yeah, I mean, physical or natural as opposed to mathematical, for instance.
Not really. I mean, do these people ever actually alter accounts of what it is to be a physical object, or actually alter an account of it to be concrete?
Yes.
That's not an account. If what you did was an account, it's clearly false. So I think before we should, I think a lot of this stuff you should just push back a lot more strongly than you do, because like the basic argument, I really don't understand how it's on the ground, but just ignoring that, I think if someone can argue against these accounts by talking about what it takes to be physical or concrete, I think they go into account of what that is, and let's hear it. And I think it's so unclear how to make sense of this distinction. I don't see how they can get an argument off the ground to this distinction.
I think the people this was referring to it would say, my ontology is about things in space and time. Therefore, they are concrete. Everything which is in space and time is concrete, or causal even in some sense. Again, a bunch of particles moving around according to a dynamical law, and they are in space, they move with their dynamics in time, therefore they are complete. Your stuff is completely clear.
I mean,
you see,
space is in space, and space is a physical entity. I mean,
no. Think about
the way a field is, you know.
Think about a very Functionalist ontology, a bunch of particles with spatial relations. And the dynamics is given by the change in the spatial relations. That's all. That's the ontology. And it's physical and not mental or whatever. Why? Because it's related by spatial relations. End of the story.
Yeah, and that's a fine ontology to have, but how this is going to get turned into an argument against people who deny that that's fundamental ontology is a question. And I don't see unless they're just kind of blatantly, you know, question how they can, you know, get an argument off the ground without giving an account of it. It is to be physical, and it seems like, you know, if anything should count as physical theories, you know, the theories that fundamental physicists are actually, you know, taking seriously moving forward. They don't involve like irreducible or anything like that.
I think it's a bit more complicated than that because there is no one-to-one mapping between the mathematical representation and the physics. There is a lot of stuff in the math representation, in the math structure of the physical theory that doesn't correspond to anything. And the whole business of philosophy of physics or interpretation of physics is just to discern, to make the distinction between physically salient, relevant, whatever, and mathematical surplus. And these people would say, no, wave function, spin equal states, Hamiltonians, this is mathematical surplus. Your ontologies must be about, and this is a priori to some extent, about stuff in space and time. And my criterion of concreteness is being in space and time. It's a clear criterion. What is in space and time is concrete physical, what is not physical.
Yeah, I mean, I would just point to the quantum gravity as a counterexample to that account of what it takes to leave the that would be, I mean, this is, it would be absurd to say that physicists are, you know, fundamental physicists don't know what, you know, they're putting forth a non-physical theory. I mean, I don't want to stipulate, like, if anything that's going to count as a physical theory, it's like fundamental physicists are actually.
I think there's many counterexamples to what you just said. Many very good physicists just put forward crazy ontologies, which just are incoherent or make any sense or difficult to grip or whatever.
Well, this is not non-physical. It just means that I have these other features. I'm trying to help you. Let me help you. But I mean, I guess this is my point. Like, it would be nice to. I mean, it would be just something maybe to add. Like, you know, if they're going to argue based on. Or put it this way, you know, there's been a lot of, you know, struggling about to give an account of what physical object is. It's an entity, let alone a concrete entity. And I think it's perfectly fair for you to point out that if someone's going to argue against you by appealing to it, they need to do better than just appeal to this kind of common sense, like, oh, I can make it.
It's difficult for me because in my heart, I think I agree with you. But as Chris said, I can assure you that there are audiences where it's going to be very, very, very difficult to make the points.
Tell me the define as well.
Again, because many people say just living in space and time.
Question. So would you agree that even if you put aside the question of what it means to be concrete versus abstract or something like that, there's still an important unfulfilled task, namely that any one of these approaches to formulating a quantum view of gravity has the obligation to show us that, you know, given whatever ontology they postulate and however they describe, whatever mathematics they use to describe that ontology and its goings on at that level, to show that from the interaction of these micro-constituents, or whatever you want to call them, somehow emerges, of course, the sort of the world as we experience it, the large-scale structure of the universe, for instance, in this case, right? That's an independent task that would still be owed, of course.
I guess it depends on, you know, different challenges. I mean, sometimes you phrase a challenge, it seems like a global thing. Like, how do we experience, how do we, you know, get the macroscopic world out of it from quantum gravity? That seems a lot different, maybe a lot easier than saying, okay, where do I find this table in and with quantum gravity. Maybe that can't be done. Maybe the best we can do is kind of these kind of global things. I mean, maybe sort of physicalism we get here is just a global physicalism. I can give you a theory such that any world that replicates, how things are according to that theory is going to replicate everything else. So look at there, that's all we need to say in order to convince us that we've done our job in explaining how you derive the macroscopic from the microscopic. I just have a broader question of, what is actually the issue? What's the challenges that needs to be met? Because,
I think I need to come back to that, but just Nick, if you had something to say.
The sound's not all that good, especially from the audio, so I just want to make sure we're following what's going on. So it sounds like there was some skepticism that anyone would deny the sort of functionalist picture in the first place, and then you were naming the guilty parties.
No, not quite. There was some skepticism in the audience that we would owe an account of what it is to be concrete versus abstract, and show that the sort of the entities that are postulated in the ontology of the quantum theory of gravity are concrete according to that definition, and that this definition was the functionalist. So there were specific, I think, skepticisms about it being the sort of definition you gave, and moreover whether we would need to give any definition at all.
Okay. I mean, when I had my hand up to start with, I think it was to say exactly the same thing that you said earlier. I mean, what the real point is to actually tell the functionalist story about how the non-spatial-temporal, partially non-spatial-temporal stuff ends up looking like it's spatial-temporal. And I think one shouldn't forget about trying to get tables out of it. I mean, I think getting something like chunks of space somehow out of it is both technically difficult, but I also think philosophical. I'm just repeating what you said. I mean, it's a philosophical issue as well. Because the functionalist. One thing I think to think about is the functionalist story should be in some sense a general story. You might end up with a whole bunch of inhomogeneous derivations of this bit of space-time structure, that bit of space-time structure that don't hang together in any principled way. Trying to understand the sort of general rules that govern those derivations and thinking about what kinds of fundamental stuff, what concepts apply at the fundamental level in those derivations, even of particle scattering events, or little chunks of space-time is a non-trivial technical and philosophical task. So I think that's what I take from this talk, and I like some of the bits where Vincent was sort of really addressing those parts of addressing those things, specifically how are they functionally related, seems to be the real takeaway message. And I think that's more or less what you were saying in your last response, Chris.
I think we would agree on that. My point was the limitation to separate the two issues and really focus on that one. I think dialectically they are different, and I think it's kind of parallel on it. But that was it. What's the ethical point?
But then there is there's a relatively small literature on this, and so far, and even two people criticizing that kind of view is something to be addressed at this point. And I think this does a nice job.
I'm still just trying to get clear on the project, but I thought finding the derivations was not like the most important challenge to meet. It is an important challenge, but it doesn't meet Maughlin's challenge, which is to show that these derivations are, quote, physically salient. And so, that's what I was attacking. Yeah, sure, it's going to be a hard matter to figure out how to, map one, the fundamental theory onto the non-fundamental theory, but then Maughlin would turn around and say, well, that's not physically salient. So what I was trying to challenge is why I think it wouldn't be physically salient. I didn't see any particularly strong reason why we should worry based on the derivations. So I just want to be clear about what that was.
So this I mean, this goes back to what I was asking Vincent right at the beginning. The sort of functionalist story, and I'm thinking about the kind of coherent story I was just sort of pointing to earlier, is going to be where the functional story about the empirical part of classical space-time theory. That is going to be the best guide and evidence you have to physical salience. It would be a mistake to think that there was some sort of a priori philosophical criteria applied there. It's going to be, as Vincent said, theory dependent, and that's the way we're going to get evidence for what the right notion of physical salience is in these theories. That's sort of a picture about scientific methodology, something like that. So in fact, it is looking at those specific stories that's going to tell us what physical salience actually is in this context.
So you don't think we can compare theories with respect to physical salience because physical salience is a very different matter, right? Or do you think all of these different classes of theories we're looking at have the same criteria of physical salience? This is a general question.
I think there's no universal notion of physical salience. Yeah, that's right. I mean,
so you don't we can compare theories with respect to it then?
No, that's right. Go ahead.
Oh.
I don't mean to speak for Vincent and Chris, but yeah, that's what I think.
The word is so you don't think you can evaluate theories with respect to it? If it's theory dependent, well, I mean, there's no theory independent notion of physical salience such that people that have different interpretations and you can criticize you on the basis of. So why not just stop?
Well, what you can compare is within the framework of the theory, a different interpretation of the theory, and compare the physical salience of the different interpretations of the theory. Okay. But then comparing the physical salience of different theories, this can be you have to find a common ground. And for instance, here I think the common ground would be to what extent one can account for empirical evidence. This is a it's going to be a general issue that any kind of interpretation of any kind of theory should be addressed. And there are people who try to give, again, the same people going to give kind of a general global notion of physical salience, namely that your theory or interpretation of your theory is going to be physical salient if it's about local neighborhoods, so things in space. Otherwise, it's not going to be physical salient. And that's what we are here. This kind of methodology that we are questioning here in the case of Functionalism, because it just doesn't mean life. But maybe just in three though.
It seems like your way to kind of the modeling criticism. So it seems like it was appealing to the general considerations about the methodology of the physical science that physical salience is going to be theory dependent notion. So if you could establish that on independent grounds, then you could undercut Baldwin's argument that appeals to physical salience by saying, you think your theory plus interpretation of independent notion of physical salience.
And basically, it's exactly what Nick and Chris do in their paper on addressing this issue in different approaches.
Okay.
So, Lorenzo?
No, I'm drawing attention.
Okay.
I just one and I think so. So you were trying to there was a certain point you have the causal as approach. You were trying to say with the generator, like how to get special temporary features out of this approach, and it's not the trivial task at all. And at a certain point you say, well, in the temporal case of the causal set, the best you can get sometimes it's just these. It's not going to get B temporal features, it's just a best B relations or whatever. So just let's figure out basically what we think of. So the John Sherman actually put forward an argument to the point that if we actually have a different notion to try to become, namely growth notion, the causal set theory could be the right way to go because the stochastic birth of elements from the null set will exactly give you the mechanism that Grob wanted in order to define becoming, right? I mean, the new layers of now successively come into existence. And of course, maybe you still have the word that you have the anti-changes, right? I mean, the one that the counter sets that are not related by the relationship, yeah, that will not probably approximate a space like hypersurface, whatever. But it seems you can get something off the ground. And I mean, we have general, you know. Okay. So what I was just since I read, no, I don't know, Chris, do you want to say something about
Yeah, that's another paper with Greg Callender, where we look at these claims and try to see to what extent becoming metaphysics is compatible with causal set theory and the dynamics of it in particular. And yeah, I mean, it's a long story, probably too long to tell you right now, but it turns out that the issue in causal set theory almost precisely replicates the problems and options that you have already at the level of classical general relativity. That's the general sort of lesson we take from that. However, there are some very interesting footnotes to that. Some ways in which it is actually different, and there's two ways in which it's different. One is that there is some hope that at least sort of on a small scale, and a scale that probably cannot emerge at the sort of larger scales, you can have something like privileged hypersurfaces and things like that, like a privileged notion of some spatially extended presence. But it is very limited. It is very limited by the fact that at the larger scale you still should be able to get some sort of theory where you have more symmetry. That's the approximate valid symmetry of the world. So that's one thing. But the other thing, which is even cooler when you look at the dynamics, is that you see that there's some sort of shadow existence seems to be possible. So it seems possible that there's a becoming which sort of sequentially, a growing space-time of which large parts are indeterminate as to whether they do in fact exist or not. Because you know that some part of this has to exist. I mean, it's not it's not an epistemic problem, it's a metaphysical thing. So there's metaphysical determinacy as to which part of a large chunk of the space-time region exists, but you know that some non-vanishing part has to exist, and that this is growing, that part that is. And then every now and then, depending on the global structure of the causal set, it can snap into determinate existence. And now you do have a partial sort of block that exists at this moment of time. Then you go on, then more sort of indeterminate stuff comes into being. It's kind of a very strange but metaphysically interesting picture that you can see there. Yeah. But these questions are sort of orthogonal to the concerns here.
I just think that you can get some temporary features.
Yes. Oh, sure. Yes, of course. Yes. Yes. Yeah. Absolutely.
To some extent, I think the case, besides this kind of reason, the case of causal set theory is different, but very different from the case of quantum covariance. And that's precisely the reason why we also consider these cases that they are completely different and different.
That's right. That may not have come out, if you don't know much about quantum gravity, maybe that wasn't so clear. The sort of the pictures you would see look similar. The Hofstad diagram of the spin foam, it's kind of dots with lines between them. So, but actually, the theories are very, very, very different. Yes, in a number of ways. And so really what the project is here is you have to address these questions for each of the theories individually. And in string theory, again, it looks completely different. Yeah.
Maybe another question for you too, Chicago. to what extent do you think this kind of framework, conceptual framework of this kind of functional story could be applied in the case of string realities and in the case of string theory in general?
Well, the reason for that, I mean, in string theory, prima facie, it looks like you introduce a more traditional space-time in the beginning. However, the dualities can undermine a straightforward picture of that. And then you have to figure out still how does the kind of effective space-time rise in string theory? How do you resolve those kind of apparent ambiguities? And also another thing is that it might very well be that M theory, which is supposed to be a deeper underlying formation of string theory that is generally considered to be part of the same research program, might very well not introduce any space-time in its original formulation. But no one really knows how to formulate that theory yet. So there are a number of different ways of doing that. And then these kinds of issues become relevant basically in the same way. If you think of it based on these things, both kind of from the string theory perspective, how the dualities undermine a straightforward understanding of the space-time theory, and also if string theory would have a deeper formulation that doesn't postulate space-time in the beginning. So yes.
Can I have a go?
Sure.
So I totally agree with what Caso said. I just wanted to add one other case, which is what I am working on at the moment, to do with existing formulations of string theories. I totally agree about dualities, and that's part of the story. But I think what string theorists sort of have in mind in this regard is when you have string scattering, which is supposed to be a story about a pair of strings coming in and somehow interacting with each other, and other strings come out in various states, and that's supposed to be the string theoretic model of particle scattering, sort of quantum field theory by energy physics scattering, and so there's spatio-temporal information built into those scattering processes. For instance, what the space-time background is will be, the outcomes that you'll get will be sensitive to what the space-time background is. Maybe in particle content, with things like angles and momentum that particles have coming out. So that's the sort of classical space-time side, how you might be reading proper classical space-time out of structures out of string theory. On the lower side, well, because of the dualities that mess with sort of metrical properties of the space-time, how big it is, mess with the topological properties of the space-time, how many dimensions it has. You don't clearly have that space-time built in. And the other thing I guess that they added when we're talking about is it's not I don't even without dualities I wouldn't be quite so quick to say that there's a classical space-time built in, because the quantum field theory story is you can sort of start with a range of different possible classical backgrounds and then get the curvature you want by having the right state of the string. So one of the string particles is the graviton, one of the gravitational field, and I don't know. The received wisdom is you can build up different curvature and deform the space-time you start with by graviton states. So that gives you that the graviton field is, I guess, playing the dynamic role of curvature, I would say. So there is that functional story, classical curvature, classical geometry. So even in that way, there's a functional story to tell. But just to bring it back very specifically to this talk, what I am specifically talking about here, as I said, is scattering processes. particles or strings coming in, particles or strings coming out in a certain way. So that very is, that very much is what's happening in the dynamics of the string theory, corresponding to what's happening in the dynamics of high energy physics and classical background. So it fits very well with this dynamical functionalism that Vincent was talking about. Is that okay?
Yes. Thanks. Maybe one last question.
I think this is relevant to the list of the Constitution objection. I'm just trying to get clear on like what sort of functionalism are you trying to get into? Like, so usually, like functionalism about mental states will say what it is to be in pain is. So I mean, they're trying to get like a something like necessary insufficient conditions plus other stuff for being in pain. So my question is are you trying to do that with space-time and entities in space-time? Are you saying like this is what it is? Like you might have thought that there was some, you might have thought there was some non-functional specification of what it is to be in space-time or to be a person or that thing, but you're wrong. It turns out like everything in the macroscopic realm has a functional definition, or are you merely, you're not saying anything about that, like a table can, contingently occupy the table role, but it could have occupied different roles in different worlds. You see my question?
Yeah, I see that.
I think it's relevant to Alyssa's objection because the argument might be something like, unless you're willing to get to say, these functional definitions and space-time entities are what they are, then there's no reason to think that the functional reduction is going to go through this could just be contingently playing that role. And so I'm not phrasing myself well, but I guess I read Alyssa as kind of saying since that sort of functionalism can't be true, then we haven't shown that we're actually getting our tigers to it, unless you want to define like what it is to be a tigers to play a certain role that can also be played by things in your fundamental ontology.
Yeah.
It's a genuine question.
I think part of it is going to be theory dependent, I think, but if you have a broader perspective, I think with respect to usual classes of space and features, then you would be committed somehow to the kind of position you just described. What we thought were genuine, three objects located in three spaces actually really amounts to something else playing the kind of functional role you take for being three objects in free space. Yes. But my point was to say that these space-time-like roles of function played by these more fundamental entities might not exhaust the nature of the entity at this fundamental level. Why? Because precisely the quantitative theories aim at describing something beyond these space-time roles. The space-time roles are just there, one of the stories just there, from the physics point of view, just to have these just consistency constraints with the normal physics, and from the conceptual point of view, to make the connection with the empirical evidence as the kind of argument, objection that or worries that people might have. But of course, the physics might want to go beyond that and give more from the description. And then the next question is, of course, is this kind of description functional as well, and so on, that this is maybe, I don't know, it's a different type of question. There are people who think that all kind of properties or physical properties are functional in the end and so on. But this is some kind of tangent to what you're saying. I'm not sure.
Yeah, I mean, it wasn't quite a coherent question, but the thought is that, I mean, standard argument against functionalism and philosophy of mind is that, I could still be in pain even though it had different effects effects. So I could imagine someone saying, like, unless you're really saying that what it is to be a table is to play, such and such really complicated causal role, then where, saying something else plays that role is not enough to get us table. Unless you're willing to
say that there is nothing more than functional description.
Yeah.
But I think in the end we will be committed to that somehow. Yes.
Okay. I was really just trying to.
No, I see the point. You want to add something?
Yeah, no, I think that's right. Anyway, okay. I think we've come to the end of this. We're already over time, so please join me in thanking Leslie.